Welcome everyone. Thank you for joining us for part 2 of Leader's webinar series IP 101 for the operator and engineer. I'm Kristen and I invite you to send me your questions in the chat box during the webinar. Now I'll turn it over to Steve Holmes.
Thanks, Kristen. Hello everybody. We want to thank you for joining us this morning as we walk our way through some of the different pieces of IP as we go through this. One of the things we're going to be covering is using the Leader 5600, 7600, or the Fabrics QX and SX tag to be looking at physical layers. We're going to look at what happens with IP packet errors. What is this little thing dealing with RTP packets, and some of the data you can pull out of an SFP that might help you in doing troubleshooting. We will be having more webinars come up. If there are topics, specific topics that you guys feel are in definite need, please let us know in the chat window and we'll see about adding those to the list of webinars that we're putting together for this series. One of the things you got to remember that IP is just another I/O interface. It's just another way to get data from one point to another point, or into a switch or out of a switch. In SDI, we've always looked at, for physical layer, we've always looked at I and jitter, SAV, AV placement, CRC errors, and doing pathological testing to find unique issues that cause the SDI to break up. IP is very similar, but the things we're going to be looking at are optical power, CRC errors, RTP errors, and what a switch does with corrupted packets, because there are some unique things that happen with corrupt packets in the IP world that make troubleshooting a little unique at times. So those are the things in this series we're going to concentrate on. It's just how do we do this that has changed in what's going on. The things to remember about ST2110 is there are multiple flows. There is an independent video flow, there is an independent audio flow, and an independent data flow. And some networks and some organizations, these three items may actually start on completely different networks that get joined together in a switch, and when you join them and bring them into a single flow. So some of the errors or some of the things you may look at for troubleshooting may actually end up branching off into independent switches and independent networks. One of the things to remember is nothing has really changed about troubleshooting. The I/O has changed, but how you start hasn't really changed. It's still a divide and conquer. We still go to the middle of the network. We still need to cut the network in half and say, hey, is the issue coming into me or is the issue leaving me? And it will help you turn around and take care of half of what you need to do. So you go to a point in the middle, you say, is it coming into me or is it leaving this point? Or is it still good here? And so that means it's on the other side of where I'm at, and you've already cut half of your work in half, rather than trying to start at the beginning and go through every single network component one by one all the way through. So in IP, we have several pieces that have checksums in the Ethernet packet. So we have the Ethernet header, and then we have a frame check sequence that encapsulates the entire packet. So if anything happens within that packet, data gets corrupted, data gets lost, it gets mangled, you will have a checksum error. And you'll be able to see that you have a bad packet. So there is a CRC value that is incorporated into the FCS, the frame checksum, and the receiver is going to take that same IP packet, it's going to calculate a frame check sequence and see if it compares to what the original transmitter put into the stream. If they compare, the packet's perfectly good and everything moves on. There's also independent checksums for the IP header portion and the UDP checksum portion of the packet. One of the very unique things, though, about IP is if we have good data coming into a switch, we have no packet errors leaving that switch. But if all of a sudden something happens along the way and we end up with packet errors going into the next switch, you will not see those packet errors coming out of that switch. Errored packets are dropped and are not propagated through the IP network. This can make troubleshooting a little unique. One of the reasons that we can't propagate these packets is we really don't always know where the error is, and if the error happens to be in the destination address, these packets of video could end up, or audio, could end up in the wrong location or in the wrong service. So we don't want that to happen. So it's set up as part of the protocol of IP that a switch will not propagate errored packets. You will have a loss in data, but you have to know how to look for that loss of data downstream. This is where RTP comes in. So within real-time protocol, RTP, there is a sequence number. And it's very much like what we did in MPEG, where we had a continuity count. And you could use the CC count to detect drop packets by looking at this count sequence and see a misstep in this sequence. Now, the other nice thing that the RTP header does, if somehow packets get out of order and they're still there, as long as they fall within a given buffer size, and that's up to the receiver does have the ability, if they incorporate it, to reorder the packets back into the proper order by looking at this sequence number. But if the out of sequence packet is larger than your buffer, or if it is dropped data, you will have errors. So we are going to have to rely on the RTP packet sequence number and look at sequence errors using the RTP header rather than the IP header once it has propagated through a switch. So what we're going to end up with is we have good data going into a switch. We have no RTP errors coming out of a switch, no RTP errors all the way through our network. Then if we have that data hit and we end up with error data going into that top switch, we will have RTP errors leaving that switch. We will not have frame check sequence errors or IP errors. We still have the loss of data, but using the RTP count sequence, we can now detect that we have lost data and you're going to have to rely on RTP errors in order to troubleshoot things that have gone through more than one switch. The other thing, like I mentioned earlier, is in some cases, the -20 flow, which is our video flow, the -30 flow, which is our audio flow, may actually originate in separate networks that come to a aggregation switch that is where you're going to join both of the flows and take them onward to wherever your destination happens to be. So your troubleshooting may lead you back down a path to where only one of the flows happens to be in trouble. And this would be an indication where you have either just audio errors, the clicking and popping of drop data, or you have just video errors and the audio is absolutely perfect all the time. And none of the errors are ever dropping on top of the audio. Now, the errors will always affect the video more than they're going to affect the audio, just because of the ratio of video packets to audio packets. So it can get a little tricky going back, but you do have to remember that you may have to look at different flows and different points to see some of this when they actually split into individual networks here. So when we have situations like we have remote venues, remote things happening, and we have, in this case, let's say a truck out at a sports venue, and it is giving us a 2110 feed into our leaf spline network that we happen to have, and an error happens back in the truck or back in the feed to us somehow. Again, you will not see any packet errors being propagated through that network, but you will see the RTP errors if you look at the RTP sequence counters. Different instruments show this in slightly different ways, but that's what you're going to have to use in this new IP world to be able to find issues and to be able to find that I do have errors, because now those errors will be propagated as RTP sequence count errors. So when you plug in your waveform monitor and you start monitoring that IP flow, as I've indicated on this diagram here on that far right-hand leaf, the IP packet errors will be 0 unless that feed just coming to me is in trouble. But the RTP sequence errors will track all the way back to the source of the issue. So we can use either our Leader products or the Fabrics products, since Leader now owns Fabrics. And we can turn around and error check from the source through the network all the way to the destination and be able to track these errors using the different waveform monitors that we have at our disposal. One of the things Fabrics does have is this beautiful little handheld, the SX tag, which allows you to actually plug into a switch and bring that switch in, that data in. You can do an IGMP join, or it will respond to NMOS and set up the flows. And that allows you to get into, behind the racks, move to different locations within a switch or within a patch bay very easily, a lot easier than lugging a entire waveform monitor around that you got to find power for and possibly another screen for. So it's a very, very handy way to do this. One of the unique things is because of the way 2110 works and the way different vendors incorporate how they recreate the picture, we could get different errors because one packet in HD makes up approximately a quarter of a line of video. If you drop that packet, in some cases, as the bottom left-hand corner shows, and I'll show you a bigger shot of this in a second, everything may be shifted from that point down to the bottom of the screen because you've dropped that packet, and now all of your TRSs, which are your EAV, SAVs, your start of active video, end of active video, my sync points, are all in the wrong location from that point down to the bottom of the picture. You may have what we get very similar in SDI, where we get pixel errors, but in this case, you're going to get pixel errors the size of the packet, and you'll see these little white striped lines all through your picture. Or in some devices, every time you get an error from that point down, the picture actually goes black because it can't reconstruct the picture from that point because all the SAVs and EAVs are in the wrong location. So the indications you get on a picture monitor are going to vary from device to device just based on how they reinterpret the data coming in and recreate the video. So in this particular shot, you can see that Lady Liberty is sitting there, and she should be in the middle of the picture, and the bottom end of the statue, we took an error and lost that one packet, and everything from that point on shifted to the left because of the drop of that packet, and all the TRSs ended up in the wrong location, and the picture wrapped around because of that drop in data. And this ends up just jumping all over the screen horizontally. It just sits there and just jumps all over the place on you. If the raster is always kept intact and you're filling the raster, much like what we do in MPEG with data, what you're typically going to get is these little stripes. I hope they come through the Zoom session here, but you can see that there's stripes of just wrong data, wrong pixels in the picture. And you will get, every time there's an error, you will get these stripes of bad data in the picture, indicating that you have drop packets and the data is not correct. Some of the devices will actually, as I mentioned before, drop to black, either from the point of the error down or the entire screen. Every time you get an error, they turn around and either the entire screen or from that point down go black. And that's honestly pretty common to happen when they lose the packet and they can't find the data in the correct location. The picture just ends up going black from that point down. So it is moderately common and very disturbing, much more so than having things show up as just little errors in the picture, like that one. So how do we look at these particular errors on our newfangled waveform monitors that have IP in them also, so that instead of looking at eye and jitter, we end up looking at the proper data for the IP flow. On the 5600 and 7600 from Leader these are going to be under the status screens. And if we bring up the status screen, we will get the IP flow table. And in the IP flow table, it's going to show you the different IP streams that you are joined, which input they are joined into, and then the link data over on the bottom right-hand side. So in this case, we're actually looking at 403G inputs, which is going to be over 10 gigs. So this is actually a 25 gig link. And it is giving you that bandwidth data as the packets going across the bottom, which should always be consistent. That's one of the things you want to look at, is that bandwidth in the chart is absolutely the same, because the bandwidth should not be changing unless you're joining more flows or dropping flows. And then the other thing happens to be the error count window. So right below the bit rate there, if 10.45 gigabits, you will see the FCS errors, the IPCS errors, and the UDP checksum errors. So those are looking at those yellow blocks there. The main one is the top one, which is the frame sync error, which is looking at the entire IP packet and looking for checksum errors in that packet. So it will have error counts for both link 1 and link 2. If you're doing 2022-7, you'll have link 2 up, and you can see the error counts in either one of the two links. But as I said before, we need to be able to look at RTP errors. And in the leader products, they indicate RTP errors on the packet arrival screen. So they're looking at the packet arrivals and they're checking the checksum counts in the RTP header. And if there is an error in that checksum count, it will be indicated by red in the packet arrival time. And you'll see some of these packets are jumping up high, and some of them are down just a little bit above 7.5 microseconds. Some of them are going up to 15 microseconds. And that indicates an entire packet is dropped versus a packet that's just errored. So the time between two packets has doubled because the packet is missing. So that's what that indication going up to almost 15 microseconds is, that the entire packet has been dropped. It's been lost. The ones that stay down right around 7.5 microseconds are just indicating the packet's actually in error as it's gone through the system. So you can take these charts and look at from 2 minutes out to 72 hours. So if it's something that someone has complained about that you had a hit in data, you can go back to the chart and expand the chart out and see at what time you had the error, and then start investigating, okay, what else was going on at that point in time? Did we have other maintenance going on? Was this going on, that going on? At that same point in time, to be able to look at these things. When you work your way back to the actual errors that are coming down the fiber, and you actually take that fiber and plug into the waveform monitor, then you'll be able to see the frame check sequence errors. And the frame checksum errors is indicated here in red in the bitrate graph will pop up, and now you'll see those errors on the main status page. But like I said, If you're looking at a switch and the errors are before the switch, you will not see those particular frame sync errors because the switch is going to turn around and drop those packets so that it doesn't propagate bad packets that we aren't sure about what the source and destination fields look like, so that the packets don't end up in the wrong place. Because if you think about it from multiple standpoints, we really don't want to propagate bad packets because, you know, multicast is used for bank transactions. The last thing you want is to do a deposit, have it land in somebody else's account. Or if little Johnny is watching, you know, some children's TV show, and all of a sudden you take a packet error and they get a frame of the channel, you don't want things to happen like that. So we have to drop the packets. The other thing that we can look at is the SFP data. And one of the things here happens to be the type of SFP you have plugged in for the type of feed that you're going to have. So on port 1 in this case, I do have a 25 gig SFP28 plugged in to the waveform monitor. On port 2, it happens to be an SFP plus, so it's at 10 gigabits. Both of them are multi-mode at 850 nanometers, so you want to make sure that the bit rate is correct for the network that you're going on, and the wavelength is correct, either multi-mode or single mode. You haven't plugged in the wrong type of SFP, you know, for a single mode network on a multi-mode system. And then right below that, the RX power, the receive power. Now these aren't calibrated, you know, power meters, but they are really, really good indications. You really should look at these and get very familiar with your network and what is the normal power level that an SFP tells me, because if something has happened to a connector or a fiber has been damaged, you can actually see that, you know, I should be coming in at, you know, -3, -5 dBm, and all of a sudden I'm coming in around -11, -12, which in a lot of cases, -12 gets down to the point where the signal actually starts getting in trouble with a lot of different SFPs. So I can't tell you on multi-mode or single mode what the power level is, because it depends on the transmitter and it depends on the sensitivity of the receiver. But for the ones you buy, you really should characterize and find out where your system is running and what power levels I should have in, because that's going to give you a good indication if something has happened in the physical path that causes this issue. If you've had an error from, you know, a connector getting munched or a fiber getting crushed, but it's still getting a little bit of data through. So let's, on the Leader 5600, take a look at this data coming in. So this is my system here that is actually up and running live. You can see on the frame sequence checks here, I have no frame errors coming in. I have no IP checksum errors, UDP checksum errors happening at all. And like I said, I'm not going to see those unless I'm looking at the actual data itself. But if I go over to my packet jitter, this is where I'm going to look at the arrival time of my packets. My packets are coming in all nice and clean. They're all at the same time, which is what you'd expect from a normal loading on a switch. but we can go back in time, and I can look at much larger periods of time. If I look at the last hour, last 2 hours, you can see that a little bit over 100 minutes ago, I did have a RTP error. I had a hit, and that happened to be when I was setting up my demo this morning that I created that error. But you can go back in time and look at those particular errors and see how far back they happen to be in going here. So if I move back and try to set up my network here, we'll see how this goes. It's always fun on live stuff. I have created an error there in my data that you see. If we were looking at the picture would have jumbled all over the place. But if I go back to my error count, my FC error count, I see absolutely nothing. In this case, I did pull the fiber out, put the fiber back very, very slowly. So you actually do see the dip in bandwidth, but during that whole dip in bandwidth, I didn't take any checksum errors. And the picture is going to break up differently just depending on how we look at different things. So if I try to just barely give an error here, let me go over to IP. There you saw the errors. So I was looking at my feed, and that's one of the great things about the 5600 waveform monitor. It's got 4 inputs. The first 2 I've got set for SDI, so I was actually looking at the SDI feed, and I was breaking the fiber. So you can see the breakup in the picture there. That happened when I actually ended up taking that error. I had no errors in what was going on. And if I look at the package window, you can see right there between 40 and 20 is those last errors that I caused that picture breakup that never showed up on the actual packet windows. So like I said, one of the other things that we can look at is data from the SFP itself. And you can see that my receive power is minus 3 dBm. And if something were to happen to my fiber, you'd actually see that decrease. So there you see it go up to 10 dB, come back. Now, this is where I'm feeding directly into the waveform monitor from the switch. And I'm at 8.711. And we're still okay on the picture. And see during that time if we took any. We did not take any errors during that period. It's up to 11. If I was to go over that, I would start taking either frame sync errors or RTP errors or both. So if we go here and in your troubleshooting, you finally get back to where you're looking at the actual data and the actual cause of the problem, then you're going to start seeing, you can see I just took a whole boatload of frame sync errors there. So now that was an interruption of the feed to the waveform monitor from the switch. So that would be like a source or another switch feeding the next switch. The source that is your playout server feeding the switch, and you're looking directly at that source. Then you will see those frame sync errors. And then that does let you know you are looking at the actual source of those particular errors. If we pop back here to the presentation for a second. Let's take a look at how we see these same errors and same error conditions on the Fabrics QX product. So in the Fabrics, if you hit the Fabrics menu down on the bottom, you'll see the menu come up with all the different analyzers that you have available to you. The row to the right of the Fabrics button shows you which analyzers you currently have up. You can actually mouse over each one of those and they'll tell you. And then right underneath of that are the saved presets that you may have set up and saved. I have several different analyzers and screens set up here. The ones that are important for finding physical layer issues here are the SFP network status, the IP receive flow select, and the picture and the SFP input network here. So we can turn around and look at different things. It might be nice also to have the audio up, the system IO up, maybe the PTP data up, but you can have many, many different windows up and move them around and put them where you want them. So under the SFP network stats, what you will see on the Fabrics product is received packets and good packets. Now, these numbers may not be the same when you get to the box or set the box up, but what you're looking for here is those numbers stay, the difference between these two stay absolutely consistent. And this is actually looking at that FCS, that frame check sequence. And again, these numbers are not going to increase unless you are looking at the fiber that actually has the error on it. These things will just tell you that, hey, the packets that are coming to me are all good packets. I've had no bad packets coming to me. So again, we need to look at the RTP sequence errors. And in the receive flow, which is the flow table for the Fabrics, the right-hand column is sequence errors. So that is the RTP sequence errors. That's the one you're going to want to look at. That's the one that's going to tell you 1 to 5 switches down the line, hey, I have errors coming to me. So it will count off the errors. It should be sitting at 0 as it does on the top picture with no RTP errors. But on the bottom one, you can see that it has had different RTP errors. Now, one of the nice things Fabrics does for you is it does actually break out and it tells you which flow. Is it my video flow or my audio flow that actually is taking the errors? And in this case, you can see that for one error on the line, I got 15 video packet errors and only 2 audio packet errors. So that tells me that since I had errors in both the video and the audio, that my point that I want to look at is still where both of these two services are together. It's before, or excuse me, it's after the 2 networks were separate networks from each other. So if we turn around and take a peek here, here's the Fabrics QX. Up in the top left-hand window here is that packet count. And if you notice up by my mouse pointer, that the numbers are exactly the same. So there has been absolutely no packet errors on the physical line coming to the unit. Down on the bottom, because this is monitoring the same feed as I was just putting errors in, you can see all of the RTP sequence errors that I have put in the system when I was showing the errors on the 5600, the Leader LB 5600. You can see how many video errors I put in there and how many audio errors I put in there. Now, in order to reset these counters right now with the Fabrics, you have to reboot the box. And when you reboot the box, it will zero the counters out and start the count out for you nice and clean. But those are the two windows that you're primarily going to want to look at. Then the other thing that you'll want to look at is the picture and what those errors look like in the picture. So if I double click on the picture, it will go from the small window to a quarter size to full screen. And when I have it up full screen, you may not see these errors come through, I'm not sure. But I just got some little itty bitty packet errors when the input went away and when the input came back. So those counts have increased now because of those errors I just introduced into the system. But if we look up in the top left-hand corner, the numbers between the packets, as far as good packets and received packets, is still exactly the same error count because the switch dropped those packets and did not pass those packets down to the end of the system here. I would have to turn around and actually be on the feed itself to get those numbers to change. So now I just put errors into the feed going to the QX, and now you see a difference in those numbers at the top left of the screen. And that was an indication that, yes, I had the actual packet errors. So I am now looking at the source of those errors. So let's go back here and look at the Fabrics tag. The tag is a beautiful little box. It does allow you to look at SDI. It does allow you to look at IP. And it will show the errors as picture breakup. The SFP module that we have to use to get the IP into the box does not pass a lot of data about the errors that are actually coming in. But what we end up with is picture breakup in some form or another. So the tag is one of the devices that the entire picture pretty much breaks up when we have the error, because we lose data coming into it, and you will get that picture breakup. But the beautiful thing about this box is its ease and portability of being able to take the tag to multiple locations, get behind racks, get where you need to go quickly, and with just battery operation, you don't have to drag anything around. You have to plug in and power up. That you can take it. You can see the form factor is very, very nice for being able to do this. So things to remember about all of this. Again, IP is just another I/O interface. In looking at this, we just have to think slightly different when we think about this I/O interface. The IP frame sync errors do not pass through a switch, only the RTP sequence errors will. And if you happen to be in a 2022-7 one-for-one redundancy, you should not see any errors in the picture at all. You'll still have a problem on one of the flows, but the packet picker should be grabbing the good packets from the flow that is still good, but you still have a big issue on your hands that you need to go correct. And if you're only getting video errors or only getting audio errors, go back and look at your network layout and see if those two turn around and divide and come from individual separate networks. If they do have separate networks, or you have an AES-67 network going off to an audio console outside of the switcher, then that's going to tell you exactly where you need to go, and that takes 3/4 of your troubleshooting and part of that divide and conquer that I talked about earlier. So I hope this has been beneficial for you. I hope you got some good information out of today's webinar. And Kristen, if we can take a peek at some of the questions.
Absolutely. Thank you so much, Steve. We do have some questions here. One of them is, for a 2110 decapsulator device, does PTP in any way control or affect the flow of output data packets out from a decaps buffer?
That's going to get into the internal workings of that decap. As far as I know, no. It's just going to put the timestamps on them and, you know, pass them back to you. And it should only be involved in the reconstruction if it's a decap and make an SDI back out of it, aligning the video and audio to the same point in time, looking at the 2110 RTP timestamp of what frame the video was created in, and putting all those audio packets back in line with that frame.
Another question, can you record or stream out log data to an external destination so you can have historical data?
Yes, on the leader boxes, you can dump the log file. You go in and you dump the whole log file. If you want it streamed, there is the ability to do SNMP traps, and you can actually have traps going out the door to a trap server as the errors happen, and you'd get your long-term historical data from the SNMP traps that were sent out.
Is there any way to inject the analyzer in the data paths between switches without doing a physical patch?
No. The only way to look at things in the middle, unless you have a 1x2 IP splitter, is to actually plug into a switch, do an IGMP join, and look at the data.
The next question is, for ST2110, how much time between packets, PIT, is too much? Is there a value, or does it just depend on the decap device?
It depends on the receiver. It's just like SDI. Every single SDI receiver is different in how much, you know, in the case of SDI receivers, it's typically how much jitter they'll withstand and how much line loss they'll withstand. There's pretty much no standard on what they should do yet, other than in 2110-21, they are going through that standard and building buffer models that the source should stay within, so that you can build receivers to be able to handle what the source is doing. And that is going to be one of the future sessions I have, is looking at packet delay, looking at buffer models, and looking at what happens when those things fall over.
Does vertical offset timing measurements change with 211020 now that there is no VANC, V-A-N-C? Are we still required to offset against house PTP?
You really can't change the offset. The offset should be the length of your vertical interval. So PTP actually starts where black starts. So it's going to start at line 0 and pixel 0. But the RTP timestamp of the first active pixel of the first frame is going to be the length of the vertical interval. So typically, if you're HD, it's going to be 21 lines out for the first RTP timestamp. So there are timing screens that most of the 5600 has, where we can look at what is the RTP versus PTP timing, what is PTP versus black timing. So PTP and black timing should be on top of each other. RTP versus PTP should be 21 lines out, or HD, 42 lines out for 3G, and it just gets progressively bigger because your vertical interval gets bigger.
What is VRX and CMAX?
Oh, sorry, I had those up. Those are HDR readings that I had on the screen. So the CMAX is the looking for what is the highest pixel value in any one frame. The Vmax is what is the average pixel value across the frame. And those were for post-production, and those are HDR measurements. I was doing some HDR work earlier, and I didn't shut those off the picture on the leader waveform monitor.
That is all we have of the technical questions. We did get a question of if your slide deck would be available, and so we can share that on social media. We will make that available. Also, if you were not able to attend the first part 1 of IP 101 for the operator and engineer, that is available on Facebook. We'll put that link in the chat box again. We did get some questions about that.
We want to thank you guys for attending. I hope we gave you some good, usable knowledge today, and I want to thank everybody for attending, and have yourself a great and safe rest of the day.